I do mean it. I'd love to come sometime. And I don't think I've ever been to Africa, let alone, it's abysmal. I've got to improve my my adventure-ness. All right, so I've got a story here. I've probably got way too many slides, so I've got no desire to get through them all. So just feel free to jump in at any time and ask any questions. I'm quite happy to go on detours or tell you more about something or less about something. So whatever.
Great. This particular seminar forum is all about detours, and so expect questions and you can go on as until you give up, more or less.
The more the better. The more questions, the better. All right. So it's based on a paper I wrote with Shlomo a year ago and a follow-up paper from a couple of months ago. And it's a really basic question in quantum field theory. And it's been a nice project for me because it's a question that I really thought I knew the answer to. And it turned out for 20 years, I was completely wrong. So the question is, how do you give chiral fermions a mass? Or said another way, take some massless fermions. Any dimension. I'm mostly going to be in 4 dimensions. I think I'm entirely going to be in 4 dimensions in this talk, but there's various stories in different dimensions. Take massless fermions. It is a true fact that massless fermions always have more symmetries than massive fermions. So take massless fermions, give those massless fermions a mass. And the question I want to ask is what symmetries get broken when you go from the massless to the massive fermion? So a very, very basic question. Let me give you some examples to just sort of set the scene. 4 dimensions, free fermion, free Dirac fermion. A Dirac fermion, when it's massless, splits up into 2 Weyl fermions, a left-handed and a right-handed Weyl fermion. And there is a U1 squared symmetry. There's a U1 that acts on the left and a U1 that acts on the right. If you give them a mass, the mass term involves a left-handed and a right-handed fermion joined together. So if you give them a mass, one combination of those U1s gets broken and the other combination survives. So the combination that survives is the vector U1. That means it acts in the same way on the left and right-handed fermions. And the axial or chiral U1, I don't think I can do it with my fingers. Is that right? No, that's I literally can't make my fingers go in opposite directions, but the axial or chiral U1, which acts differently on left and right-handed fermions, is broken. All right, another example. Our world famously does not respect the symmetry of parity, and that manifests itself by the fact that the left-handed and right-handed fermions transform differently under the standard model gauge group. Left-handed fermions transform under the SU2 weak force, right-handed fermions do not. What that means is that in the standard model, it's not possible to write down a mass term for any of the quarks or leptons in our world. And of course, very famously, nature achieves this by coupling to a scalar field. So in our world, because the gauge symmetry now, rather than a global symmetry, because the gauge symmetry is chiral, meaning left and right-handed fermions transform differently, you cannot give a mass to the quarks or leptons in our world directly. Instead, you couple to a scalar field. The scalar field, of course, is the Higgs boson. When the Higgs boson gets a VEV, this Yukawa term turns into a mass term. But also at the same time, when the Higgs gets a VEV, it breaks the gauge group. It breaks SU2 times U1 down to a U1. So again, another situation, if you give fermions a mass, you break chiral symmetries that transform left and right-handed fermions differently. And the question I want to ask in this talk is this always the case? Is it possible to give fermions a mass without breaking chiral symmetries? In particular, in this example, is it possible to find another mechanism, one that nature seems not to have chosen, that would give quarks and leptons a mass without breaking electroweak symmetry, preserving this full gauge group? That's the question I want to ask. Of course, it's only an interesting question because the answer is yes, not no. So I'm going to explain how you do it as we go along. Before we get there, I want to tell you why I care about this. So I'm going to spend the next 10 or 15 minutes just giving you some motivation for this question. And the motivation comes from something I've sort of been quietly obsessed with for for years and years and never done anything about. It's the Nielsen-Ninomiya theorem. So the Nielsen-Ninomiya theorem, I'll review it shortly, is a statement that you can't put chiral gauge theories on the lattice. When you try to discretize time, space and time, this is an obstacle. It's a topological obstruction towards putting chiral gauge theories on a discrete space and therefore being able to simulate chiral gauge theories. It strikes me as an absolutely astonishing statement. I mean, it's if you take this at face value, this is the statement that we are not living in the matrix, regardless of what Elon Musk says. And we cannot be in a computer simulation because it's impossible to simulate the laws of physics on a computer, according to the Nielsen-Ninomiya theorem. So I just find this, an incredibly powerful theorem. It's a true theorem, of course. Clues in the name. It's a mathematically correct theorem, but somehow it must be wrong. It must be wrong in the sense that it's too powerful. The conclusions are too strong to be believed. So the large part of why I'm interested in this is to find a way to evade the Nielsen-Ninomiya theorem. So let me sort of spell this out in a little more detail. I'm going to give you a baby proof of the Nielsen-Ninomiya theorem. I'm not going to do it in 4 dimensions, although it's not too hard. I'll do it in 2 dimensions. So what's the story? Space is now a line. And in 2 dimensions, the notion of chirality for massless fermions is much easier than in 4 dimensions. There's no handedness issue. In one space dimension, a massless fermion goes that way at the speed of light, or it goes that way at the speed of light. And what we would like to do is try to put such a chiral fermion, say just a right-moving fermion, on a lattice. A lattice meaning discrete space or discrete space-time. All right, so everything is dead easy. It's just free fermions. On the left-hand side here is the dispersion relation, the energy versus momentum relation for a single right-moving fermion. So what's going on here? It's a line with a positive slope. It's a straight line because it's massless, so its energy is proportional to momentum. And the slope is positive because through, I guess, Hamilton's equations or the group velocity, the velocity is the derivative of the energy with respect to the momentum. So this is a right-moving fermion, the velocity is positive. This would be a left-moving fermion that goes the other way. Something just to be aware of here, this sort of picture where we've got positive and negative energy states is the Dirac-C picture, which is not really the right way to think about quantum field theory. It's useful in certain contexts. It's the correct way for condensed matter physics. It's not really the correct way for relativistic quantum field theory. That's actually going to be important a bit later, but bear with me. All right, so if we're in the continuum, there's no problem at all in just having a right-moving fermion. Here's the dispersion relation. In fact, my sort of more rigorously leaning friends tell me that you can actually define this quantum field theory at the level of rigor of a mathematician. Because of course it's a free field theory, but it's just got a right moving object. So there's really nothing wrong with this quantum field theory. All right, now comes the next step. We're going to make space discrete. So space becomes a lattice point. Lattice spacing is little a. And I think fact number 1 in any solid state physics course is when space is discrete, momentum becomes a compact variable. Okay, momentum becomes periodic. Because we're all string theorists who know more about Kaluza-Klein compactifications than we do about condensed matter physics. The Fourier transform of this is slightly embarrassingly more familiar to all of us. So if space is compact, momentum is discrete. Momentum is quantized. Well, the Fourier transform is that when space is discrete, momentum is compact. What that means is that you have to draw this dispersion relation on a periodic circle. So the horizontal axis now, the p-axis, is periodic. It's a circle. And your energy versus momentum had better be continuous. If it's not continuous, bad things happen after Fourier transforming. You get non-local quantum field theories. So what that means is that we have to draw this line for low energies, but at some point, in particular the point pi over a, momentum pi over a is equal to momentum minus pi over a, and what's gone up here somehow has to connect with what's down here, just to have a continuous energy versus momentum graph. The way that happens if you just take a Weyl fermion, discretize it naively, is you'll find the following dispersion relation. Things go up as they did before at low energies, or low momentum, I should say. But at some point, the energy momentum relation turns over, and there's another crossing of this E equals 0 axis. This other crossing happens at the edge of what we call the Brillouin zone in condensed matter physics. It happens at pi over A or minus pi over A. Any questions? All good? All right, so what's the upshot? We started by trying to put just a right-moving fermion on the lattice. That's this guy here. But the lattice doesn't allow us to do it. The lattice rebels and it gives back new low-energy states. They're low-energy states because the dispersion relation necessarily crosses the E equals 0 axis. They have high momentum. They have momentum equal to 1 over the lattice spacing. But at least as far as quantum field theory is concerned, at least interacting quantum field theory, they have low energy, and that's what's important. For example, if you look at loop diagrams in an interacting quantum field theory, these objects will necessarily come in at arbitrarily low energies, particle-antiparticle pairs. Of these objects. Notice, moreover, that we started with a positive slope, but the second time it crosses the axis, it has the opposite slope. Opposite slope means opposite moving fermion. So this is a left moving fermion. If we start with a right moving fermion, the new object is a left moving fermion. All right, so this is the essence of the Nielsen-Ninomiya theorem. There's a fairly straightforward generalization of this to 4 dimensions. The idea is exactly the same. Excuse me. And the theorem comes in sort of 2 separate parts. The first part is it is not possible to put a single right-moving fermion on the lattice. The lattice will rebel and insist that there's a left-moving accompanying fermion. That's often called a fermion doubler or a mirror fermion. And secondly, it's not possible to put a chiral gauge theory on the lattice because any force that the fermion at the origin experiences, the fermion at the edge of the Brillouin zone will also experience. I'll actually say a few words about how one can evade that conclusion, maybe a bit later in the seminar. But for now, the way to think about it is just that these 2 objects, the left and right moving fermion, weren't independent. They came from the same underlying field. You can see that they're connected in the dispersion relation. So if you couple this one to a gauge field, this one will also experience that gauge field, unless you work very hard to somehow try to evade that.
So David, can I ask a question?
Yeah, please.
So when you said earlier that you can't simulate physical reality on a computer and tie this to the Nielsen-Ninomiya theorem, is this a statement that you always end up with this fermion doubling problem unless you break something specific, or I mean, how did you mean this inability to simulate nature in this context?
So as a prerequisite to simulating, I'm assuming that you need to make space-time discrete.
Okay, that was my question. Whether you have to put it on the lattice and okay.
It's all to do with the lattice. One might think that perhaps there was a way to simulate with continuous space. Time is sort of an irrelevance here. We can do this in Minkowski space, Euclidean space. It can be continuous or discrete. That doesn't matter. It's really space being discrete that's key. I don't know of any proposals for how to keep space continuous and do a simulation. It's sort of the 0th step. It's not that we don't have a fancy algorithm to do it. It's that we don't even know how to do the 0th step of discretizing the laws of physics.
Okay.
Other question?
Yeah, question.
George.
There's a paper here by Trivedi saying the Nielsen-Ninomiya no-go theorem is false. What is your response to that point?
Which Trivedi?
Anil K. Trivedi.
Then I'm less worried. It's not a false theorem. It's a true mathematical theorem in the sense that it's been proven at the level of rigor of a mathematician. You may ask the following: are there certain loopholes? As always, no-go theorems in physics are as powerful as the assumptions. Is there a particular assumption that one can one can do away with so that you don't show it's wrong, but you try to evade it. There are many suggestions on how one can do that. So I don't know if this guy is trying to do that. That's what this talk will be about as well. I'll tell you what I think is the weakest assumption of the Nielsen-Ninomiya theorem and see if we can prove it.
Thank you.
Other questions? All right. Maybe this will be useful later. I might not get to it. We'll see. But there's another version of the Nielsen-Ninomiya theorem. The essence is the same. The details are different. And it's a beautiful idea due to David Kaplan in the 1990s. David suggests that if we try to simulate massless fermions in, say, 4 dimensions, the right scenario is to actually look at massive fermions in 5 dimensions, which seems odd. But the trick is that your 5th dimension should be an interval. And if you just look at the Dirac equation, the solutions to the Dirac equation of a massive fermion on an interval with suitable boundary conditions, you'll find that you get massless chiral fermions localized on the edges. So this is this really dates back to work of Jakiv and Rebbe for 0 modes of domain walls. Subsequently work of Callan and Harvey about anomaly inflow. But David showed that all of this goes through on the lattice. So you can have on your interval left-handed chiral fermions on one edge and right-handed chiral fermions on the other edge. You've still got the doublers, they're still left and right. But rather than having them separated in momentum space, they're now separated in real space, albeit an extra dimension over the one that over the 4 original ones that you thought you cared about. So it's a useful way of rephrasing the problem, and I may or may not get to why it's useful later. All right, so this is the obstacle that we have to overcome. And as I said, there's a bunch of assumptions that go into the Nielsen-Ninomiya theorem. And many people have written papers on how one can try to evade this. Here's the one that I think is the deepest and the most interesting. It's that one of the assumptions of the Nielsen-Ninomiya theorem, and in fact, not one that they wrote explicitly in their paper. They had a bunch of assumptions in their paper, but this is not one that they listed, is that it assumes weakly coupled quantum field theory. In fact, not only does it assume weakly coupled quantum field theory, the actual proof, the proof that I just showed you, relies on single particle quantum mechanics. You know, the whole proof was written in the language of Dirac, where I've got negative energy states that are filled here with some Dirac C and positive energy states here. This is a useful heuristic language. And it's the correct language for single particle quantum mechanics, but it's not the correct language when you have strongly interacting quantum fields. When you have strongly interacting quantum fields, they're single particle states sort of go out the window at some stage. There's particle antiparticle pairs, which can have very low energy. The whole fields are fluctuating strongly. So the real, what I think is one of the key loopholes is that if somehow you can make these fields strongly interacting, either when they get to high momentum or on one edge of this interval, then the whole language in which we prove the Nielsen-Ninomiya theorem basically goes out the window. And we could try to come up with a way to evade this issue about having these low energy states. So this is an idea that goes back to Eichten and Preskill in the 1980s. And they suggested the following. Maybe there's a way to turn on some strong interactions. The strong interactions, as I said, would only affect the objects in yellow, localized either in momentum space or in the extra dimension. And the goal is that when you look in this region of momentum space, all states have a minimum energy. And the same over here, all states should have a minimum energy. In other words, you want to take these particles that appear to be massless and you want to gap them. Gap is used to only be used by condensed matter physicists, but now high energy physicists have started embracing it. It just means give things a mass. The gap being the gap between 0 and E equals mc squared in the spectrum. So that's the idea of Eichten and Preskill. It comes with a couple of challenges, but Jeff turned his camera on, which probably means he has a question. So I'll take that first.
So there was a very funny exchange. I think Xiaogang Wen posted on his Facebook page, or I think he posted on his actual web page, that he had proposed some solution to this problem as well, and try to get it into PRL. And the referees were very, very, very scathing. This is a highly contested corner of quantum field theory, as I understand it. And part of the contestation was precisely that Acton and Preskill didn't quite achieve what they'd set out to achieve, and Xiaogang Wen didn't at all achieve what he was claiming in the paper.
Let me tell you about the two challenges, and then on the next slide I'll tell you why things failed, why Zhao Gang's thing has not been proven to succeed, why referees are scathing. I can address all of this.
Great.
So what are the two challenges? Well, one is to somehow find a way so that only, say, the high momentum modes experience these interactions. So you want to give masses to the doublers, but you want to leave the original guys alone. The second one, actually, maybe let me just sort of fill in some context. Suppose you wanted to simulate the standard model. What would you do? You'll take all the quarks and leptons that we know and love, and you'll put them at the origin here. So that actually the diagram's a little bit misleading, because at the moment everything at the origin is right movers and everything here is left movers. You'd put right-handed fermions and left-handed fermions at the origin. There'd be the mirror pairs, mirror fermions would appear. The idea is you want to give masses just to the mirror fermions. Okay. Now the second problem is the following, that we want to simulate a chiral gauge theory on a computer. That means that the fermions here at the origin, and I've lost my cursor, there it is, the fermions here are chiral fermions. Let's say the fermions of the standard model. That means the objects here that you want to gap are also chiral fermions. They have the opposite chirality, but as a collection, they're chiral fermions. And you want to give them a mass without breaking the chiral symmetry. Because if you broke, say, the chiral symmetry, the gauge symmetry, the fermions at the origin would know about it, and they wouldn't feel that gauge symmetry. So these are the two obstacles you have to overcome. One, you have to localize the interactions so that only the doublers experience them. Two, you've got to find a way to turn on interactions that gap the doublers without breaking the symmetry that you care about, this chiral symmetry, say electroweak symmetry in the standard model. All right, so what happened? So this is going to address Jeff's question. Eichton Preskill suggested the following. You see, you want to give these objects a mass, but you can't just write down a mass term, because a mass term would break the chiral symmetry. So you have to do it through interactions. They suggested turning on some 4 fermion interactions. And the idea being that you can't write down quartic interactions that preserve the symmetry, but you can write, I think I said that wrong. You can't write down quadratic interactions that preserve the symmetry, but you can write down quartic interactions that preserve the symmetry. If you can't, maybe psi to the 6 interactions or psi to the 8, but at some point you can write down a string of fermions that preserve the symmetry. In fact, Eichton Preskill suggested adding a bunch of derivatives here. The idea being that when you've got derivatives, high momentum modes experience the interaction more than low momentum modes. And if you're a continuum quantum field theory person, like I am, and I think all of you probably are, the first thing you think is that this can't possibly work. You know, this 4 fermion term is irrelevant. Irrelevant terms, by definition, don't do anything in the infrared, and they're certainly not going to take a bunch of fermions and make it massive. But on a lattice, hey, Jonathan.
Can I ask you a very simple question there? So you talked about putting in derivatives, which would then affect the high momentum terms. But here we're not talking about high momentum. It's a sort of specific region of the momentum space that you're interested in, presumably.
It's as high as it can get, though, because of course it's periodic.
Right. Okay. Okay.
Yeah. So, but you're right. It's not a strong cutoff. And you know, with derivative terms, these things feel it weakly, and then it gets stronger and stronger as you go up. You could also try and do it here, and by turning on maybe some coupling, which depends on the x5 direction, is 0 here and is strong there. So there's various ways you can try and implement this. So what happens in the continuum? No possible way this can work. On the lattice, you could take the coefficient here, which is dimensionful. It's an irrelevant operator. And you could crank it up so it's strong at the lattice scale. Now, when it's strong at the lattice scale, all our continuum intuition sort of goes out the window. It's just a bunch of qubits on the lattice interacting in some complicated way. But you could hope that in principle, and I should stress in principle, there's nothing to stop this. In principle, you could hope that this strongly coupled lattice interaction would do what you want and give masses to these fermion doublers, leaving these guys alone. I think it's a wonderful idea.
Sorry.
Yeah, please.
Dave, can I ask a quick question before you move on to that? In the extra spatial dimension case, have they considered using warping to do that?
Yes, you know that there's a lovely paper by Chabachaki and others who I don't remember. I'm probably Chaba's mates like Yuri Sherman and Martin Schmaltz, and okay, it's some subset of these people, and they consider warping. They claim it solves it, but no one's ever pushed that idea forward. And I have to confess, including me, partly because the first half of that paper is absolutely beautifully written and summarizes the problem in the most wonderful way. It's really where I learned a lot of these issues. And somehow then I never read the second half of the paper. So there is a proposal out there, but it's not one that Lattice people have taken seriously. And it's not one that I've looked at as carefully as I should have done. A fact which I had to admit when I gave a colloquium at Cornell and Chapper asked me about his paper. So yeah, it's a great question. So yes, they have, and somehow it's just faltered. It's one of those things where it just seems to be a dead end in the literature, but I think it's worth resuscitating somehow.
Okay, thank you.
All right, so what goes wrong? By the way, it doesn't work. It doesn't work. It doesn't work in the sense that it's a brilliant idea, and when people actually tried to simulate, it just didn't work. So what happened? Well, when people tried to simulate, they found different phases. In some phases, everything became massive. In some phases, everything remained massless. In some phases, this became massive, but at the expense of breaking the chiral symmetry, which just happened to spontaneously break anyway. But you never found the phase in which this became massive. These were massless, and the chiral symmetry was preserved. I think I understand why. I'm not a lattice gauge theorist, but I think I understand what's going on here. You see, we have this intuition in continuum quantum field theory that the psi to the 4 terms are irrelevant, because they are. And psi to the 6 terms are more irrelevant, and psi to the 8 terms are more irrelevant, and so on and so on. When you crank up the coefficient here so that you're strongly coupled at the lattice scale, all of that intuition from continuum quantum field theory just goes out the window. You want to make the psi to the 4 terms relevant, but that means the psi to the 6 terms are also important, and the psi to the 8 terms are also important. And moreover, there's no hierarchy between them. There's no reason that psi to the 128 is less important than psi to the 4 once you've gone into this strongly coupled at the UV cutoff regime. So I think what's happening here is that this whole proposal should work, but somehow the phase you're looking for is a point in a very high parameter space. It's not enough to consider psi to the 4. You probably have to consider psi to the 6 and psi to the 8, and there's no reason why that terminates anywhere. So no one knows how big the high dimensional space is. And I think that what's going on is just no one's managed to find the point in this high dimensional space where you get the physics that you want. I think, but like I said, I'm not an expert on lattice gauge theory, but that sort of strikes me as the issue. So it's been checked by many people. There have been many sort of variations on this idea. One such variation was by Xiaogang Wen in 2013, and then a sequences of papers by Wang and Wen. What to say? The one that Xiaogang's upset about because he got the really awful referee reports. I'm sort of with the referees. You know that he had important ideas, but it was all in the language of group cohomology and anomalies, bosonic anomalies, fermionic anomalies, and he was selling it as a solution to a problem that has long been known in an entirely different community. And if you want to claim to have solved that problem, you've got to give it in the solution in a language that community will understand. In particular, this particular problem, there are many claims over many years that people have solved it. You want to claim to have solved it, simply simulate and show that you get a chiral fermion on the lattice. That strikes me as a very fair requirement. Xiaogang didn't get beyond group cohomology statements. So I'm very sympathetic with the referee reports. You basically just say this. The subsequent papers by Xiaogang and Juven are much more concrete in their proposals. I think they're very interesting. They mostly focus on 1+1 dimensions, where the problem is slightly easier. It's more or less the same idea as Eichten and Preskel with some twists. Again, there's no reason it shouldn't work except for the problem that no one's actually simulated it. And this issue about the high dimensional parameter space. Does that answer your question from earlier, Jeff?
Yes, thank you. I mean, the Juven and Xiaogang's papers are equally difficult to read because they're all posed in the group cohomology setting, right?
Do you know what? One of them is really nice. I don't know if it's the short one or the long one, but one of these Wang Wen papers from 18 is really lovely and very clear to read. Yeah.
Cool. Thank you.
All right. And I'm going to move away from the lattice now. Any questions about this whole setup? How am I doing for time? All right. Any questions? Okay, so what do I want to do? I want to address this challenge of how you give chiral fermions a mass without breaking the symmetry. I think I understand what the problem is here. It's because we're resorting to strongly coupled effects at the UV cutoff. And so what I want to do is find a way to give chiral fermions a mass within the language of continuum field theory. Okay, the idea being that continuum field theory is always weakly coupled at the UV. You flow to the infrared. Things can become strongly coupled in the infrared, but and we have to sort of find a way to deal with that. But you still get to use ideas of Wilsonian RG, and you also know that you don't have this infinitely large parameter space. You know exactly what the parameters are in the UV and what they do in the infrared. So that was the goal of what I'm about to tell you. All right, I should also just comment, there's a name for this property. The phenomenon of having chiral fermions, giving them a mass, but not breaking the chiral symmetry goes by the name of symmetric mass generation. There's actually a bunch of different names, all in the condensed matter literature, but this one I think is the nicest. So symmetric mass generation means take a bunch of fermions, transforming chirally under a symmetry, give them a mass without breaking the symmetry. It was first understood by Fidkowski and Kitaev for certain discrete symmetries, but it's been an ongoing project in the context of topological phases of matter for the last 10 years or so. All right, so let me tell you what the issue is. We can go back to those two examples at the beginning. There is an obstacle towards taking chiral fermions and giving them a mass. And the obstacle was understood long ago by a Toft. So Toft introduced what we now call the Toft anomaly. And it's the following. Take a quantum field theory with a global symmetry G. For these purposes, G is just going to be some simple continuous symmetry. A lot of the progress in recent years has been thinking about G as a discrete symmetry, and we have various examples in the papers, but here we'll just keep it simple. G is a global symmetry, a continuous symmetry. Toft told us that to every global symmetry G, we can associate a number, and that number is called the Toft anomaly. So what do? You put, in 4 dimensions, you put currents on the 3 edges, you sum over all chiral or Weyl fermions running in a loop in this triangle diagram, and you just read off there's some momentum dependence of this diagram, you just read off the coefficient in front. All right, it's worth contrasting this with various anomalies that you might have heard of. If this Toft anomaly is non-zero, there's nothing wrong with the symmetry at all. If this Toft anomaly is not non-zero, the current is still conserved, the Hilbert space still decomposes into sectors with different charges. If this is non-abelian, all states fill out multiplets of this non-abelian symmetry. Nothing wrong with the symmetry at all. The case where the symmetry doesn't survive quantization is the ABJ anomaly, and it's where you have two gauge currents on the edges. However, if the Toft anomaly is non-zero, it means you are not allowed to gauge this symmetry. You're not allowed to couple it to a gauge field, because then the gauge symmetry would not, in the presence of that gauge field, the gauge symmetry would not be good. That makes the theory inconsistent. Now, the importance of this number was stressed by Toft. It's that you have a quantum field theory with a symmetry group G, and the number, the Toft anomaly associated to that symmetry group, characterizes the symmetry in the following way. Whatever you do to the theory, deform it in some way, add extra fields, let it flow to strong coupling in the infrared, whatever happens, if the symmetry survives, this number, the Toft anomaly, does not change under any deformation. That's what Toft taught us. So what does it mean? It's a wonderfully powerful statement. So if you have a global symmetry where there's a Toft anomaly which doesn't vanish, you can say immediately, without knowing anything else about the theory, that there have to be massless particles in the spectrum. Have to be massless particles in the spectrum because if you go to low energies, you have to recover the Toft anomaly. For certain discrete groups, you can do that with topological quantum field theories, but for continuous groups, you cannot. What that means is that two things have to happen in 4 dimensions. You have a continuous symmetry with a non-vanishing Toft anomaly. Either the symmetry has to be broken, in which case you get Goldstone modes in the infrared, or the symmetry has to survive, in which case you have to be able to find the Toft anomaly at arbitrarily low energies, but that can only happen if there are massless fermions that carry the Toft anomaly in the infrared. So it's really a spectacular statement. You calculate something completely trivial, it tells you immediately that there have to be either massless bosons or massless fermions in the infrared. All right, what does that mean for us? It means that, remember, we want to take a bunch of fermions transforming chirally under some symmetry, compute the Toft anomaly for that symmetry. If the Toft anomaly is non-vanishing, there's no possible way you can give those chiral fermions a mass while preserving the symmetry. Because if you look below the mass scale, there's nothing to pick up the anomaly. What that means is that for the first case I had, there's no way to take a single free fermion and give it a mass preserving the axial symmetry. Just can't do it. However, if you have chiral fermions and the Toft anomaly vanishes, then there's no obstacle, at least in principle. Then it should be possible, or at least Toft tells us it's not impossible, to take that set of chiral fermions and give them a mass while preserving the symmetry. Now, a vanishing Toft anomaly is also needed if you want to gauge that symmetry. So what this means is that in principle, you should be able to take any chiral gauge theory, including the standard model, and give the fermions in a chiral gauge theory a mass, but without breaking the gauge group. That's simply a conclusion from these basic ideas of Toft. So that's what I'm going to show you how to do. It's not important that you gauge the symmetry G. It could be global, or gauged. But as long as the Toft anomaly for G vanishes, it is. I want to say, let me say it differently. As long as the Toft anomaly for G vanishes, there should be no obstruction to giving fermions a mass preserving G. In nearly all cases that I've looked at, I figured out how to do it. There's actually one case where I don't know how to do it, but I suspect it's because I'm not smart enough rather than there's some real obstruction. All right. I'm going to give you some more details about how to do this, but are there any questions before we go on? All right. So let me tell you the punchline, and then I'll sort of fill in some of the details, and then maybe to end the talk, we'll get to a concrete example where we see how things work. What's the deal? You have a bunch of massless chiral fermions. This is energy scale, by the way, this axis. Bunch of massless chiral fermions, and I want to find a way to give them a mass. I can't write down quadratic mass terms because they're chiral, and so left and right-handed fermions transform differently. It would break the symmetry. For now, these can just be free fermions. I think that's simplest to think of. I can't do what Eichton and Preskill wanted. I can't give 4 fermion terms because 4 fermion terms are irrelevant and they don't do the job. So what's going to happen? What we're going to do is we're going to deform the theory in some way. We're going to deform the theory in a very specific way. We start with the massless fermions, and we add, in addition, some very heavy degrees of freedom. These very heavy degrees of freedom are vector-like under the symmetry, which means there's no problem giving these extra degrees of freedom a mass. And in particular, there's a dial in my theory. It's just the masses of all these guys. And I can make these as arbitrarily heavy as I like, decouple them from the dynamics, so I'm left just with the massless degrees of freedom that I started with. What I'm going to do, though, is change that dial. So my heavy degrees of freedom start to come down and become lighter and lighter. At some point, they start interacting with these chiral degrees of freedom. And those interactions are going to be such that everything becomes massive, with the symmetry group that I care about being completely unscathed. That's the game. So what's going on? Again, chiral degrees of freedom to start with, vector-like degrees of freedom up here. You know, it would be cheating if I took chiral and conjugate chiral and gave a mass term and just declared success. That's not the way this works. It's chiral fermions plus vector-like fermions. You dial smoothly in parameter space and everything becomes chiral. In other words, the punchline is this rather surprising sort of pseudo equation in the box. It's that a chiral theory plus a vector-like theory can, under certain circumstances, be a vector-like theory. Another way of saying this, which is a little bit surprising, there's no such thing as a chiral gauge theory. You know, if you're given a partition function, there's no way to determine whether it's a chiral gauge theory or a vector-like theory. The only way to determine, or the only way to characterize a symmetry is the 't Hooft anomaly. For a chiral gauge theory, by construction, the 't Hooft anomaly vanishes. So therefore, there's not really any way to distinguish it from a vector-like theory. That's kind of what's going on here. All right. Here in more detail is how it's going to work, and then we'll actually do a proper example. So take a bunch of chiral fermions. I'll give them all different names. There's a bunch of left-handed fermions, a bunch of right-handed fermions. They transform under different representations of the symmetry group G, so I can't put any pair together to give them a mass. What I'm going to do is introduce a new confining force which acts just on some subset of these fermions. And I think, just for the sake of argument, let's take it to act just on the left-handed fermions. The goal is to find a confining force that binds these left-handed fermions together into new massless composite fermions. I stress that's not so easy to do. It doesn't happen in QCD. In QCD, you don't get massless protons and neutrons, you get massive composite fermions. Get massless pions, but they're bosons and they don't do the job. But you want to find some dynamics that's going to take these fermions and bind them together into a new left-handed fermion, something like this, that is necessarily massless. Moreover, you want to find a way to do this so that psi nu transforms under G, and I've said something a little bit wrong here, should transform under G in the conjugate representation from the guy that was just sitting out this confining dynamics. The idea being that then you can write down a 4 fermion term like this. It's going to be a 4 fermion term with a small coefficient in the UV, unlike Eichten and Preskill. You think it's irrelevant because it's a 4 fermion term, but it's an example of what we call a dangerously irrelevant operator. That means it looks irrelevant in the UV, but as you flow to the infrared, strong dynamics, strong coupling dynamics kicks in, and it changes the dimension of this operator to make it from irrelevant to relevant in the infrared. In particular, if these 3 bind together, it changes it into a mass term in the infrared that gives a mass to this new fermion and this guy that was just sitting everything up. If we could achieve this, everything gets a mass. The symmetry group G is unbroken throughout, and we've succeeded in doing what we want. Any questions about the strategy? All right, there's a catch to this. Let me tell you what the difficulty in achieving this is. It's that usually when you get confinement is accompanied by chiral symmetry breaking. And in the current context, me just go back one slide. These fermions transformed under some global symmetry G. There's some extra confining force which binds this together. From the perspective of that confining force, this G is typically a chiral symmetry. And therefore, if confinement is accompanied by chiral symmetry breaking, this symmetry G is going to be spontaneously broken, and that's game over. That's bad for what we want to achieve. So the difficulty in actually doing this in any particular example is finding a way, a mechanism to bind fermions together so that you do not break chiral symmetry and that you're left with massless fermions in the infrared. In other words, this process of symmetric mass generation is equivalent to the phenomenon of confinement without chiral symmetry breaking. In fact, this single sentence, I think, is the one-sentence summary of my paper with Shlomo from last year. It's the symmetric mass generation is equivalent to confinement without chiral symmetry breaking. All right, so I'm going to give an example if there are no questions about the general strategy.
Sorry, David, I have a question.
Yeah, please.
Slow at getting to the mute button. Is this a dimension-dependent statement?
It's a statement. Let me get this right. Yes, it's true in 4 dimensions. It's true in 3 dimensions if you replace chiral symmetry with time reversal invariance.
Mm-hmm.
That's the analog of chiral symmetry there. I suspect it's true in 5 dimensions, also with time reversal invariance, but I have no examples in 5 dimensions whatsoever, but I do have them in 4 and 3. In 2 dimensions, you have to be a bit more careful because of the Mermin-Wagner theorem. So if your chiral symmetry is discrete, for example, you could have a discrete symmetry which flips left-moving fermions by a minus sign, but not right-moving fermions. It's a chiral fermion parity. Then this statement is correct.
Mm-hmm.
But if your symmetry is continuous, the flavor of the problem is changed a little bit because there's no such thing as spontaneous breaking of continuous symmetries.
Yep.
So there is a story there, but it takes a slightly different flavor.
Okay, thank you.
Other questions? All right, here's my example. It's not quite the simplest example, but it's not far off. And you know, it's the standard model, so it's the one that I like best. What I'm going to do is take one generation of quarks and leptons in the standard model and tell you how you can give them a mass without breaking electroweak symmetry. I stress this is not the mechanism that nature has chosen to use. Nature gives quarks and leptons a mass through the Higgs mechanism. There's no 2 ways about this. I also don't know of any phenomenological application of what I'm about to tell you. And it's not through want of trying, but it's also fair to say I'm not a phenomenologist. So it could be that I've just not been creative enough. Nonetheless, I think it's interesting. There is a way to give quarks and leptons a mass without breaking electroweak symmetry. You have to introduce new degrees of freedom, as I've tried to stress. Let me show you how you do it. So here's one generation of quarks and leptons in the standard model. I've conjugated the left-handed fermion, so actually everything on the screen is a right-handed fermion. You can see, for example, that the left-handed quarks transform in the 3 bar because I've conjugated them so they're actually right-handed objects. All right, no fermions sit in conjugate representations. That's a statement that I can't write down mass terms, quadratic mass terms for any fermion here. Standard model is a chiral gauge theory. All right, so what am I going to do? I'm going to add new degrees of freedom, originally at some high energy scale, but then I'm going to dial the parameters, the masses of these degrees of freedom down to make them interact with everything here. That's the plan. So what are the new degrees of freedom? I've got 3 things I need to add, so I'll do them one at a time. Firstly, I need to add a bunch of fermions, extra fermions. They're written in red, but these fermions all come in pairs. So these are not Weyl fermions, these are Dirac fermions. They all come in conjugate pairs. so that I can give each pair a mass and dial it up to be as large as I like without breaking the symmetry group G. So you can see there's a 3 and a 3 bar, a plus and a minus 2. This pair is actually neutral under all the standard model groups. It's like a pair of right-handed neutrinos, if you like. All right. The purpose of adding the extra fermions is that it brings something new to the game, because when you have the extra fermions, there's actually an additional symmetry among this fermion content, which is in the green box here. So you see that in the green box, there's pairs of fermions that have the same quantum numbers under G. That means that in addition to the standard model symmetry group, there's an additional SU2 symmetry, which rotates the objects in the green boxes. Okay. You can check this SU2 symmetry commutes with the standard model gauge group. Also importantly, there's no mixed anomaly between this H equals SU2 and this U1. So that if I do gauge this SU2, standard model gauge group is completely unaffected. It remains a good symmetry. All right. Again, originally this stuff has to be heavy. The way you make gauge bosons heavy is by Higgsing them. So originally what I'm going to do is give masses to the objects in red, add a scalar field which Higgses this SU2. And then what I want to do is think about, as I've said before, just bringing the mass of all these guys down, unhiggsing the SU2 and letting some strong coupling dynamics kick in. The strong coupling dynamics being the confinement of this SU2 symmetry. Okay. So what will happen? It's a strongly coupled gauge group. It's SU2 coupled to 6 doublets. It's 6 because there's 2 in here, and there's 3 in here, and there's 1 here. Okay. We're not 100% sure what this theory does, but I think we have a pretty good idea. We can simulate it on the lattice in particular. And so that, coupled with general theoretical expectations, leads us to think that SU2 with 6 doublets confines. However, it has an SU6 global symmetry, just rotating these doublets. And all evidence suggests that when this theory confines, the SU6 global symmetry gets spontaneously broken to SP3. I'm not good with SP groups, but I think it's SP3. That's bad. That's bad because embedded in this SU6 global symmetry is actually the standard model group that we care about. It's embedded in, the standard model group sits in SU5 in the gut fashion, and then the SU5 sits in the top left-hand corner of a 6x6 matrix. So it's embedded in the obvious way. If SU6 gets broken, the standard model group gets broken. That's game over. So this doesn't work. However, we just need a small twist. And the small twist is to add some scalars and 1 extra fermion. So I'm going to supersymmetrize everything in sight. All the fermions here, I'm going to add a super partner scalar. And so they're charged under the standard model gauge group. And in addition, I'm going to add a scalar, a fermion, which is not charged under the standard model gauge group, so is allowed within the rules, but sits in the adjoint of this SU2. The purpose being that now I have a supersymmetric theory, and I can solve supersymmetric theories, and I can solve them because smart people solved them before me. So in particular, this particular supersymmetric theory, SU2 coupled to 6 doublets, was solved by Natty Seiberg back in the 90s. And it has a remarkable property, and it has the remarkable property that we need to make everything fly. This particular theory confines, but does not break the SU6 global symmetry. So when it was non-supersymmetric, SU6 got spontaneously broken. When you make it supersymmetric, very special things happen, and the SU6 survives. That means that the standard model group survives as these theories confine. All right, what does that mean? The objects in the green boxes confine. They bind together into pairs. The pairs are, they're mesons in the SUSY language, but a meson in the SUSY language really means a single scalar and a single fermion. So they bind together into new massless fermions, which is what I wanted. And at low energies, the massless fermions are just written on the bottom here. Basically, on the bottom is the different pairs I can make from any object in the green boxes. So 2 L's, for example, or an L and a D. Okay, and there's 15 of these objects. There's 15 because there's some anti-symmetry, so it's 6 times 5 divided by 2. Now comes the, whenever you do a project, there's a bit in the calculation where you just get this enormous smile on your face when you realize it works. Now comes the smile part of the calculation. These 15 objects here have certain quantum numbers under the standard model. You can calculate them easily enough. And outside the green boxes, which knew nothing about the confinement, are also 15 fermions. There's 2 plus 6 plus 1 plus 3 plus 3 bar. And the lovely fact is that the quantum numbers of these 15 low energy mesons are exactly the same as, are exactly conjugate to the quantum numbers of these objects that were sitting out the whole story. In other words, that for each one of these, you can pair up with one of these objects in exactly the way that you need. So what does it mean? If we go back to the original theory and we add a superpotential are just Yukawa terms. When you flow to the infrared, this superpotential is constructed. Firstly, let me say the superpotential is invariant under the standard model group. It's constructed so that it has 2 objects in the green box and 1 that's not. As you flow to the infrared, the 2 objects in the green box confine. And so this superpotential becomes a mass term in the infrared. And it's a mass term that gives mass to everything in the standard model without breaking the standard model group SU3 times SU2 times U1. So it's an explicit construction. You can give masses to fermions in the standard model, admittedly at the expense of introducing extra degrees of freedom, but extra vector-like degrees of freedom. But you can give masses without breaking the standard model gauge group. Let me also just mention, I used supersymmetry, but it's not because I'm obsessed with supersymmetry at the LHC or anything like that. The supersymmetry was a crutch to get some theoretical handle on the strong coupling dynamics. You can also show if you softly break supersymmetry, this phenomenon is robust. It remains true when you break supersymmetry at least a little bit. I don't know what happens if you break supersymmetry a lot, but if you break a little bit, it remains true. All right. The bells of Trinity College just rang to tell me that my time is up. This is a fine place to stop if you want me to, or I could say a little bit more. It's entirely up to you guys. It's also a good place to take questions if there are any.
We're okay for a couple more minutes. You want to take them?
All right. So what's the upshot? The upshot is that there is a way in the continuum to take a collection of chiral fermions and give them a mass without breaking the symmetry. So now the question is, can we use this? Can we take this mechanism, discretize it, and somehow implement it on the lattice so that it does what we want it to, which is to give masses just to the doublers? I should say that the right, at least it strikes me, the simplest place to do this is in this domain wall fermion picture of David Kaplan, to somehow use this to give masses just to the doublers. But by the way, the reason this is the right place to do it is because you want to localize interactions just on this edge. But quantum field theory is naturally local in position space. It's not naturally local in momentum space. So it's much harder to gap things at particular momentum than it is to gap things at localized in space. So that's the challenge, is somehow to take the theory that I have, the continuum theory, discretize it. And I stress that all the additional stuff I needed was not in itself a chiral gauge theory. So, what I want to discretize is, we say it differently. If it turned out that I could gap chiral fermions only by introducing an extra chiral theory, then that would be game over because I'd just still have the problem of putting that new chiral theory on the lattice. But I gapped chiral fermions by implementing it with a vector-like theory. So there's no problem with putting it on the lattice. The only problem is somehow localizing it on one edge and not the other. Actually, I say the only problem. It turns out there are two problems. Everything I'm about to say is unpublished work, but let me not tell you the issue with trying to localize it on one edge. Let me tell you what the extra problem is, because I think it's a serious and underappreciated problem in the lattice community. It's that as soon as you solve this, and really as soon as you solve this and manage to gap the doublers, the price you pay is that your theory immediately has a sign problem. And so you've somehow evaded the fermion doubling problem, you've evaded Nielsen-Ninomiya, but right around the corner is a sign problem. Let me explain why, and then I'll stop. This actually goes back to, this wasn't what these original papers were doing, but there is some beautiful work by a guy called Don Weingarten that I had never heard of until maybe a few months ago. Here's the general context. Back in the 1980s, there were a series of papers by Waffer and Witten proving beautiful things in a very powerful way about quantum field theory. And the Waffer-Witten theorems show things like parity cannot be spontaneously broken in a quantum field theory. That's one of their results. And they're very powerful because they assume very little about the quantum field theory. All they assume is that the measure of the quantum field theory is positive definite. That means, in particular, that when you integrate out the fermions, you get a determinant of the Dirac operator, and the determinant of the Dirac operator should be positive definite. It's the only thing they assume. At the same time, and completely independently, and at the same time, I mean literally within 2 weeks of being submitted to the journals, and I think that they knew nothing about each other, a guy called Don Weingarten used essentially the same arguments to prove a series of other theorems. The Waffer-Witten theorems are very famous, the Weingarten theorems are not, even though they really are on exactly the same footing. So here's one of the theorems that Weingarten proved. He proved that the proton is heavier than the pion, which if you know a bit of particle physics probably doesn't strike you as a groundbreaking result. But he proved it without any assumptions at all. There's no assumption of confinement. There's no assumption of chiral symmetry breaking. It's simply a statement that in QCD, regardless of the dynamics, the proton has to be heavier than the pion. And he proves it just by, again, positive definiteness of the measure, and in particular, positive definiteness of the fermion determinant. If you take Weingarten's proof and you apply it to any theory with a positive definite measure, you can always show that there's a composite scalar that is lighter than the lightest composite fermion. Any theory with a positive definite measure. And here the pion being lighter than the proton, but it's a general result. Now, to get this symmetric mass generation, the whole trick was I needed some confinement and some massless fermions in the infrared. But the Weingarten theorem says that if you get massless fermions in the infrared and you have a positive definite measure, you're guaranteed to get massless scalars at the same time, because there's always a composite scalar that's lighter than the composite fermion. Now, the only reason that you would get massless scalars is if a symmetry is broken. Massless scalars don't just arise for no reason. They arise because of symmetry breaking. They're Goldstone bosons. In other words, if you have a theory with a positive definite measure, you get a composite fermion, a massless composite fermion, only if you spontaneously break the symmetry. But I don't want to spontaneously break the symmetry. The whole goal was to do this without spontaneously breaking the symmetry. Flipping that on its head, it means that you can get confinement without chiral symmetry breaking, or you can get massless chiral fermions without symmetry breaking, only if theories do not have a positive definite measure. And these are precisely the theories that have a sign problem. So it's a chain of arguments that show you can achieve what I want to achieve, but only if your theory has a sign problem. But once you have a sign problem, you can't simulate it on a computer. It's not that you can't formulate it on a computer. We've sort of, in some sense, we've improved the problem. It's not a problem in principle now, it's a problem in practice that you can't do the Monte Carlo simulations reliably to get the answer that you want. But by the way, it's worth pointing out, because I didn't really know any of this stuff a few months ago, but in the supersymmetric theory, it's just the existence of Yukawa couplings between scalars and fermions that gives you a sign problem. So, you know, the Dirac operator is d/+m, and it's positive definite only if m is positive definite. But when you have a Yukawa coupling, it's d/+phi, and phi oscillates positive negative. There's no reason why it should just be positive. So as soon as you have a Yukawa coupling, you have a sign problem in quantum field theory. We saw I needed to introduce supersymmetry, but supersymmetry comes with Yukawa terms and blah, blah, blah. So the punchline somehow of this talk, and I have more to say about the lattice, but I won't given the time. The punchline is I genuinely think there's not a fermion doubling problem on the lattice. I think it's fairly straightforward to evade the fermion doubling problem and give the doublers a mass, preserving the symmetry. But I'm not going to convince a lattice gauge theorist of this because there's no way to simulate. And part and parcel of this is that as soon as you achieve it, your theory comes with a sign problem that you cannot evade. So I'm not sure. I'm not sure it's the most heartening result, but okay, that's where we are. I'll leave it there. Thanks very much for your attention.
Awesome, thank you.
Thanks, David. We've had some questions during the talk, but the floor is now open to any other questions.
You said there were a few examples that you've looked at and one that you haven't been able to solve. What do those examples look like?
The one I can't solve is very famous. It's SO10 with a Weyl fermion in the 16.
Mm-hmm.
Should be possible to give a mass to that Weyl fermion without breaking SO10.
Mm-hmm.
I can't do it. All other chiral gauge theories that you've heard of, SUN with a symmetric and a bunch of anti-fundamentals, anti-symmetric and a bunch of anti-fundamentals, Bars-Yankelevich, Georgi, Glashow. I just went through the literature. Any interesting chiral theory, just find a way to give it a mass, give the fermions a mass without breaking the symmetry. It was very straightforward, actually. I was helped by a lovely paper by Chabachaki and Vitek Skiba, someone else, probably Martin Schmaltz, where they classify all supersymmetric theories that confine without breaking a chiral symmetry. There's various constraints. They write down them all, at least I think they write down them all with a single gauge group. And each one of those then translates into being able to implement symmetric mass generation for some collection of chiral fermions. So you can just go through, they even have tables, you can just go through their tables and translate it directly. But yeah, SO10 with a 16, we can't do. There's a possibility that there's another anomaly. One of the things we've been learning in the last 10 years is that there are discrete anomalies that we didn't know about that also prohibit giving fermions a mass. So it's quite possible there's another anomaly that maybe that I don't know about, or maybe that no one knows about. And I don't think we fully understand anomalies. Or it's quite possible that I'm just not smart enough to do it, and there's some mechanism that I haven't figured out. So.
These particular models might be a bit too complicated, but within a DSCFT, you can break chiral symmetries by turning on these operators, which correspond to quark bilinear terms. Is there any way to reformulate this in an ADS-CFT language?
Yes. Yeah, yes, because someone asked me a few months ago in a talk, and we figured it out in real time. So what's the deal? You want a symmetry with chiral fermions. So I think that necessarily means you have, let's take ADS5. You have a bunch of Dirac fermions, massive Dirac fermions in. I don't, yeah, yes, but I can't remember. I can't reconstruct it.
I mean, the picture I have is the D7 picture, but I don't know what that would mean in terms of adding masses without breaking what corresponds to the geometrical symmetry.
But I think that's a chiral symmetry, but with a non-vanishing Toft anomaly. So it's always going to be broken if you if you gap. So yeah, the question is, I have a feeling that when you work it out, ADS sort of trivializes it.
Okay.
In the following sense, you know, I slightly provocative words, but you know, in some sense, there's no such thing as a chiral gauge theory. Chiral gauge theory is a weakly coupled description, but if I give you a partition function and say, is this chiral or not, you can't say, because if it's global symmetry, you compute the Toft anomaly, but if it's a gauge symmetry, you know, it's already guaranteed to be zero. And I think in that same sense that it sort of got trivialized once you went to the bulk in ADS.
Okay.
I think.
Cool. Thank you.
Right. Any other questions? If not, thank you very much again, David. This was a great talk. And as I said earlier, it's a great treat to have you speak. I think that's it, right? No other questions? Good.
David,
All right. Oh, George, yes. Was
I
that
was just saying thank you to David.
Okay. Great.
Thanks a lot, guys. It's been a pleasure to see you all.
It will